Good afternoon. My name is Milan Vukicevic and I'm coming from the University of Belgrade, Faculty of Organizational Sciences, and I'm a part of the team from the Center of Business Decision Making. In last 10 years or so, we were involved in many aspects of data science and many projects that were both scientific and industry projects. So on that road, we solved many problems, but we noticed a very large difference between demands of science and scientific projects and industry. And this topic is really motivated by that experience, where in last few years we are dealing with more and more industry projects, and we are getting some demands that we weren't used to when we were developing scientific methodologies and algorithms and similar stuff. So what is the problem here? We have a really big data promise, right? In many industries, and we have many tasks that are solving a lot of problems, and I want to talk and to motivate now how much money or how much human benefits we can get in different areas by implementation and application of different methodologies like segmentation, for churn prediction, for risk management, sentiments analysis, etc. And in different areas of application like healthcare, marketing, finance, banking, telco, etc. We were mostly worked in recent time on healthcare application areas, where that problem and that gap between developed methods and their application in practice is really emphasized in every way, but in other industries these are the same problems. Okay, so why is this happening? Well, we have many challenges that are preventing methodology to get to practice or to commercial software. So there is a number of algorithms developed in scientific papers, but in commercial softwares we have very few of them, especially in distributed environments and big data environments, where we are always using some methods that are developed, most of them over 50 or more years ago, like Kmeans clustering, like logistic linear regression and stuff like that. So we have other problems. We have multi-modality of data, like in this healthcare applications. We have medical imaging, we have doctors and nurses notes, so we have text. We have a large time series like measuring blood pressure, heartbeat. We have different types of laboratory tests and stuff. Then we have also a high cost of wrong decisions. So we are talking about large financial funds involved there, and we are talking about saving human lives. Other thing is interpretability of solutions, where in healthcare domain that's a must. So a doctor cannot make a decision if he doesn't understand your model and your idea. So we can have a highly accurate model based on deep networks or whatever that says, okay, you should do a surgery on this patient. But doctor will say, okay, but I don't think that is necessary, and maybe it could be counterproductive. Why shouldn't I do it if I think that I do? So interpretability is really important in this sense. Okay, so further, and this is like connected. Now we are talking more and more about prescriptive analytics, so we can do something predictive and be accurate in our prediction, but what to do after that? That's for now. It is still in most application areas. These decisions are left to decision makers, to experts in the area, but algorithms do not provide what to do if we define something, if we find something, if we find some outlier, if we raise some alert, okay, it's alert, but what to do next. Further, okay, we have big data problems, but we also have small data problems where privacy concerns are often restricting access to enough data that should be available in order to develop accurate predictive or even descriptive models, right? And in recent times, there is a really popular topic of integration of domain knowledge and data-driven methodologies and algorithms. So we really cannot expect that data-driven algorithms can solve all the problems if we put all the data as our input, right? Maybe they can, but that's very expensive. But on the other side, we have domain experts with knowledge that can say easily, okay, you shouldn't try to learn this. I know that this is not working, or you should try here more deeply, or you should try something else. And that's an interesting topic that can really boost development of and application of algorithms. This is all published in International Journal of Internet Medical Research this year, and it is a nice review of these problems and ideas for solutions of these problems. So we were dealing with different types of data, and just shortly to illustrate this, I found this expression deep and wide data. Like deep data means that we have a lot of data about one person, a lot of detailed data. In terminology of patients, we have a lot of data about one patient. So we have his medical images, his life science, we have his symptoms, we have his diagnosis, we have his reactions on different drugs, we have everything about one patient. So we have a lot of patients, and we have wide data. This was the other database that we were dealing with. That is, we have a lot of patients, really a lot of patients. This database contains almost all patients from United States, from all hospitals. But it's not that detailed. It just have diagnosis, procedures that were involved, and some demographic features. So it's mostly used for healthcare, for some trend predictions, for stuff like that. It cannot be used that much for prediction of patient level problems. So one of solutions for this, let's say, an integration of domain knowledge and experts, and really I said it wrong. So one of the problems in making highly accurate algorithms is that data scientists and domain experts cannot work together all the time. So it could be small teams, but in my experience, most of the time when I was working with doctors, okay, I have my stuff to do, he has his own stuff to do, and we don't have time to work together all the time and to exchange knowledge in order to get really useful models and to solve problems. So doctors were asked to try to use some visual data analytics software, and they were really good at that, and it was better understanding of the whole process of extracting data, what can be done, what cannot be done, etc. So here we used RapidMiner. It's a very popular open source software for data analytics, and it has that nice let's say, feature that it wraps up many big data tools. Like you can visually use without writing any line of code. You can use Hive, you can use Spark algorithms, you can use many data analytics platforms, and you can put that in hands of experts. And this scale of learning is very steep. Additionally, it has high flexibility. It has high flexibility, and you can do almost everything that you can do in if you're writing your code, because it has that sub-process and macro structure. Macros, as they call it, these are like global variables that could be used. And here is one pretty complex process that is learning several algorithms. We were using SVMs here. Automatically, he is optimizing SVM's parameters. Use that, validating it under training and testing sets. And after that, when models are learned, they're sent to final evaluation on test sets. So do like feature selection, parameter optimization, everything in one or several processes that are easy to communicate with both data experts and domain experts. And that was really interesting experiments. And additionally, there is a possibility to use these operators as a scripting operators. So RapidMiners, for example, there are several more software, but we were working with this, accepts R scripts, Python scripts, so you can use Python and R and any other programming languages that you already use. So next topic is interpretability and predictive performance. So we have these problems that interpretable algorithms are mostly not advanced algorithms, but traditional ones like decision trees, like logistic regression, linear regression, and stuff like that. We have smaller space of algorithms that we can try to use. We cannot use deep neural networks for medical experiments and stuff. So they want bytes. So another thing is that data sets are, in most cases, very wide. I mean, they have large feature space, over thousands of features that are describing one patient or whatever. So this is also not interpretable. You can have interpretable model, in sense model provided by algorithm, but if you have a lot of features, this also cannot be interpreted. So we're dealing with this kind of stuff, and this is a result for one also recent study where we were trying to predict patients' risk of mortality based on their laboratory tests. These are all intensive care unit patients that undergo to surgeries stuff, and we analyze these laboratory tests. And then we see here that most tests are done on first day of admission to intensive care unit, and then smaller and smaller number, and then this number of tests that are conducted are stabilized. So this means that at the first point, doctors are trying to test everything while they cannot find the right diagnosis. When they find the diagnosis, they are working with finite set of tests. But most of these tests are not necessary to do. Patients have hard time to do the test, and they are expensive. So we try to predict and to find which tests are really important, which tests are not, and we used a simple lasso regression. We found that on first day it's very bad predicted performance, but on fourth day we have some predictability, but this is still not good for real application. Maybe for some decision support, but not any automation. But we also did something else. We used co-clustering algorithms to make this heat map, but inputs in this heat map were really weights of lasso logistic regression. So we found this here, these weights are given by each day of admission and tests, and then we see this really large blank space where some features, some laboratory tests didn't have any influence on the outcome for the whole period of 7 days. So these tests are not that much informative. These are tests that had negative correlation, and these are tests that had positive correlation. And good thing was that when we aggregated all this and made ranking of laboratory tests, these results complied with medical doctors' knowledge. So this is one promising research. So further, this is some other study where we tried to predict risk of 30-day hospital readmission, and this is really important problem in United States because they are giving patients some guarantee of success. So if you come back in a period of 30 days to the hospital with the same diagnosis, hospital will take all the costs of your further hospitalization, and also it will pay a lot of penalties, and that's measured in tens of thousands of dollars. So this is really a problem for that. We tried here to integrate domain knowledge and data-driven methods in order to do feature compression stuff. So we used a hierarchy of diseases. We started with a simple data set that had a lot of diagnosis and procedure in itself. It was over 1,000 of features and it was really sparse. It was really sparse matrix. And regular feature selection methods didn't give us good results and good predictive accuracy. Then we used this hierarchical ontology and tried to integrate it, but by selecting only features that are under one branch of hierarchy. There is algorithm behind that. I don't want to explain it now, but we managed to get much better results than competing methods. These are some similar methods, and managed to get much better results in terms of both accuracy and feature compression space. So we used a small number of attributes to make the same thing as we could do with large number of attributes. It is like we did it with 20 features. We managed to get the same accuracy, area under curve, as with 800 features. It was a really nice result. Another research that was conducted, we were using and comparing regular lasso regression and tree lasso regression. Tree lasso regression allows us again to integrate that hierarchical ontology and to remove features that are in the same group. So we are not removing feature by feature, but we are removing features from the same group at one time. And here, integration of domain knowledge also gave good results. We have this similar performance of lasso and tree lasso, and in similar ranges of selected features, but it had a good interpretability, and this is quantified here. We really provided this quantification of interpretability, where we measured how much information in terms of predictive accuracy is lost when you are removing one feature by one feature. So by removing feature by feature, tree lasso had really smaller loss of information and predictive accuracy, and this is one other example where integration of domain knowledge and data-driven techniques gave good results. Another interesting stuff was visualization, and doctors asked which visualization and which normalization techniques are good for our data. This is some specific data. I don't want to go into that, but you can see these three graphs. This is all the same data normalized by different normalization techniques. So they are using some tools and some standard, and they are not thinking about that. Okay, I'm always using L1 metric for normalization, and that's it. But it's not always the same, because goodness of visualization also depends on data distribution beneath it, and we have the same data normalized differently with completely different distributions. For example, between these three lines here we cannot see any difference, and then we compared, we measured correlation between the data, and we wanted to see which visualization and normalization really reveals that correlation in the data that we can calculate correlation parameter. Okay, this is also some feature reduction technique where we try to do propositionalization. Propositionalization is a way for compacting data set by making different combinations of features. So this is pretty simple stuff. So we use from that initial data set with thousands of features, we try to extract some good association rules and to replace these association rules with those features. So instead of thousands of features, we have 20 rules that are inducted, and then predictions are made on these rules, not original feature sets. Have some results on that, but this demands more development. Okay, this is something about stacking, but I'm not sure how much time I have. I will go to other slides. So this was another problem. So on one side we had a lot of features, we had a lot of instances, large samples, big data, but on the other side we had a problem of small data, where we didn't have a lot of patients for one disease. There are rare diseases, there are problems of lacking of data because of privacy concerns. There is a lot of problems that demand more data than it is possible, and that's due to expensive clinical trials and stuff that involved animals and laboratory testing. That everything is expensive, and for most of the stuff we don't have enough data to try to do this big data analysis that could serve. So we had another study where we again tried to incorporate this ontology with the data, but we wanted to make virtual examples. So we had some rare diseases in the data set, and if we look at all of them, we can see here that this is frequency of appearance, and these are all diagnosis diseases. So we can see that most of diagnoses have really small frequency. If we try to predict something on that data set, in our case readmission, and this is really sparse matrix, we won't get anything, and believe me, we tried. But then on the other side, when we look at this cumulatively, these diseases with small frequencies are having large number of readmissions. We have this steep part here. So, and this is on x-axis we see number of appearance of each disease, from smaller to highest number, and here we have cumulative distribution of positive readmissions of people that were coming back before 30 days. So again, we deployed this hierarchy and the data, and we found some interesting stuff that on the same part of hierarchy, patients have different. I mean, diseases have similar output when are combined with other diseases. If you have two or more diagnoses, and if one diagnosis is from one group and the other diagnosis is from the other group, these two groups often have similar readmission rate. So we mapped that through some pretty simple and randomized algorithm, but we controlled that randomization and put virtual examples that are not existing in data set, but that we generated from the domain knowledge of the data and randomization, and we got some better results than just applying on basic data set. Okay, similarly, these virtual examples are used for situations where hospitals cannot exchange their data. So one hospital have some type of patient, the other have the other type of patients, then they don't have enough data to learn for everybody, and when some specific patient comes to the hospital that wasn't in their database, they do not have good model for them. So this virtualization of the data helped to randomize and to enable secure sharing of the data where identity cannot be extracted that easily, and also can be used with other methods for this kind of stuff. And we got better results for each hospital when we use these virtual examples, even without direct sharing the data. Okay, this is the last part of presentation, and this is things that we are especially proud of in our center, because we were starting to develop these white box or glass box algorithms for, I don't know, 8 or 9 years ago, and we see that now this, we called it white box, but now we see in the literature that there is a term of glass box design, but it's generally the same thing. I will explain what is white box or glass box, but first to motivate the problem. So through the years we have incremental algorithm design. Kmeans is developed here. Okay, probably most of you won't agree with me. Probably it's developed even earlier. Then we have its extension like Kmeans, and the difference is only in assigning points to centroids or medoids. The difference is in recalculation of representatives. Xmeans that have some hierarchical extension to Kmeans, Gmeans, MPC Kmeans, Kmeans++. Each of these algorithms have the same algorithmic structure, but has some different components. Like this Kmeans++ have different type of initialization compared to basic Kmeans. Xmeans can find right number of clusters compared to Kmeans, etc. So, but still, even with all these improvements, all agree that Kmeans is by far the most popular clustering algorithms in both scientific and industrial application, and it's really alive. And if you open any software, you will see Kmeans, but many of these other extensions you won't see, even if they showed better performance in many scientific papers. Also, Kmeans is identified as one of the top 10 data mining algorithms. Also with C4, 5, and CART, these are decision trees, and these are also very old, but still the most popular. Now, why is that? Well, Kmeans have a really nice properties. It is really simple to use. It is intuitively understandable. Low cost of computation, implemented in many environments. Kmeans is parallelizable very easily, and that's good stuff. But on the other hand, sorry. But on the other hand, there is a lot of flaws in Kmeans. It has a widely popular stuff that it cannot handle outliers well. It has a lot of randomization, so results are unstable and stuff. But it's still the most popular and most widely used. And this is the problem really of black box design, because everybody are developing their own algorithms in their own scientific environments and experimental environments, and adds something to existing algorithms. So you will publish an algorithm today. I will see your algorithm. I will try to find something that I can improve. I will show that that works on some data sets, and I will publish a paper and stuff like that. But still, that won't end up in commercial software. And this is really the problem, because there is a slow integration there. And this was one of solutions that we proposed, and this is really an application of like good software architecture to data mining algorithms, where we developed some, let's say, meta algorithm or generic algorithm. We called it generic algorithm that has all the components from K-means, or we did it also for decision trees. So general algorithm is the same. Then we identified different components that are solving different problems in that general algorithm. So we have initialization of centroids, we have distance measuring, recalculation of representatives, we have further splitting algorithms, splitting clusters in order to find the right number of clusters, evaluation measure and stuff like that. And we implemented that in software platform like this. So this really enabled combination of all existing components. We implemented a lot of components from the literature, not algorithms, but components on each part, each sub-problem of the algorithm. And we could really combine them, and we made combinatorial explosion of different algorithms with different components. So I can use a part from K-means, and part from G-means, and part for X-means, or some other combination. We ended up with over 1,000 algorithms that are different in sum of components, and we still have different parameterization for each component or sum of it. Okay, there's some other papers that are published based on this research, but as I said, we have now we have a lot of algorithms. So this was one problem. Okay, I want to find the best algorithms that will fit my data. But on the other hand, I already have a lot of algorithms, and I have a parameter optimization problem. And what should I do then? That is real problem. So we made a study of meta learning. So now we had that large algorithm space, and we had pretty large data set, not that large, but between 30 and 50 data sets. We made a data set repository. We evaluated each combination of components on each algorithm. And now we had a lot of stuff. Okay, it was expected from us to find better solutions than single algorithms, because we had a lot more algorithms, but that would be overfitting. But component-based design allowed us to do something else, to see which components are really influencing on good results or bad results. We found that some of the components, not whole algorithms, we didn't compare whole algorithms, but we said, okay, this type of initialization was good for data set that is described by its meta-parameters. So then we can recommend an algorithm and say, okay, I will recommend this type of initialization for this type of data sets or data distributions. So that was really that was also really nice result, and there was many studies in meta learning in classification and regression problems, but not in clustering ones. When we starting to explore that, we did some literature review, There were some studies that involved 5 to 10 algorithms and maybe 5 to 10 data sets. We were largely over that, so we had more than 1,000 algorithms in our and yet analyze them by each component. Similar stuff was done with decision trees, but I won't talk any further about that. We even developed some extension for that RapidMiner software that I talked about, where you can install extension and try to play with these decision trees. Like, okay, I want to design my own algorithm through visual selection of components and setting up parameters, or we even made some meta algorithm that is using evolutionary strategy and tries himself to select components, build algorithms, and optimize parameters. There are also a number of publications published about that, but it's also software solution that could be tried, and we did that with our students and when we are learning them about algorithms and machine learning and decision trees or clustering. Say, okay, this is high-level concept, and these are components that could be used, and this is how everything works. So it's white box and open. It's open, and it showed really good results, even with teaching and also with performance. So some further future work, we will try to apply these methods and try to develop new ones for on different and heterogeneous medical sources like lab tests, comorbidities, nursing notes, imaging, and there are already some studies involved in that. Further, we were working on some smart data, smart city data and problems of elderly people in smart cities, where they have different sensors involved, where they are followed constantly where they're going. If they catch a bus, they know which bus is catch. If they miss their road to home, they know that. And we're trying to make some models and predictions to early identify some problems in memories or some problems in frailty or something like that for smart cities. And further, we are really interested in development of these and integrated these data and knowledge sources, mostly in terms of ontologies or rule sets. These are some of collaborators that we were working with in last year, and it's really extensive list. And that's it for now. Thank you.